So good evening to all the viewers and participants from India, and very good morning to Professor Pamela Norris joining us from the United States. So before she takes over and gives her presentation, let me quickly introduce you the speaker. Professor Pamela Norris is the recently appointed Vice Provost for Research at the George Washington University, and this research was conducted while she was the executive dean in the School of Engineering and Applied Science and the Frederick Tracy Morse Professor of Mechanical and Aerospace Engineering at the University of Virginia. She is recognized globally as a leading expert in nanoscale heat transfer, especially interfacial thermal transport with a focus on thermal management across a range of length scales. She has served as the PI or co-PI on over 45 sponsored research projects representing well over $25 million from Department of Defense, the National Science Foundation, industry, and foundations. In 2016, she was honored with the Society of Women Engineers Distinguished Engineering Educator Award for enduring positive influence on students' lives as a gifted teacher, mentor, and role model, and for promoting greater diversity in science, technology, engineering, management, higher education. Pam serves on the advisory committee to the board of directors of the American Society of Thermal and Fluid Engineers, which are the collaborating society with for this conference with ISHMT. And she is also in the board of directors of ASTFE and on the scientific council for the International Center for Heat and Mass Transfer, the IEC HMT, and is the editor-in-chief of the Nanoscale and Microscale Thermophysical Engineering. With that, she is a very reputed professor in nanoscale heat transfer. I hope many of you already are familiar with her work. Without much delay, I would like Professor Pamela Norris to take over, and I will help her with the slide. Thank you.
Thank you much. I appreciate it, the introduction, and for driving my slides, because Murphy took over this morning and my screen doesn't want to share. So I hope everything will work out for us. So good evening to those of you in India, and thank you very much for this invitation. It's a pleasure to be here. As just described, I just recently left the University of Virginia, but what I'm reporting here are advances made over really the last couple of decades in my lab at the University of Virginia, where we were advancing the field of thermal boundary conductance with a focus on eventually getting to the point where we were able to manipulate it. So this work was done collaboratively with several former students in my laboratory, Dr. Leanne Larkin and Dr. Nam Lee and Dr. Justin Smoyer, along with collaborators from Professor Avet Ghosh's Virginia Nano Computing Group. That's Dr. Carlos Polanco and Jingyi Zhang. So I'm very grateful for these collaborations. And we just co-authored a chapter in a book, which I will provide a link to at the end of the presentation. It's just about to be published right now. So with that, let's begin by talking about thermal boundary conductance to make sure everybody's on the same page. So you're all probably familiar with the concept of a thermal contact resistance, which is what enables you as a small kid to put your hand on a hot surface without being burned, because there's so many voids and crevices, and you don't have perfect contact between your finger and that hot surface. So this is important for bulk surfaces, and it's a macroscopic quantity. But if we look on a nanoscale, there's something that exists even if you have perfect contact between two materials. This is thermal boundary resistance. It exists even at ideal interfaces, and it's because the vibrational properties of the materials on either side of the interface differ. And that's what we're going to be talking about. Next click, and that's going to give us boundary conductance, which is the inverse of the resistance, and it's the heat flux across the interface divided by the temperature drop that occurs at the interface. So why is this important? Well, here's a very graphic illustration of the effect of this very small but finite resistance that occurs at this interface. This is a high field effect transducer, and you see in that very small little layer there, when you blow it up, there is a very thin film that is on top of a substrate, and that thin film has finite thermal conductivity itself, but the resistance at the interface is enough to cause this hotspot to occur. And these hotspots are a leading factor in device degradation and failure. So it's really important that we do not neglect the additional resistance added at the interface. And even more importantly, next click, we'd like to know how to engineer that interface so that we can influence the scattering of the energy carriers, the phonons that occur at that interface. So here's an example of what the thermal boundary conductance looks like for different types of interfaces. For metal-metal interfaces, it's a fairly high thermal boundary conductance, but for metal semiconductor interfaces, it's fairly low, and it ranges over 2 orders of magnitude. And while at metal-metal interfaces, the conduction across the interface is dominated by electron transfer, at metal semiconductor interfaces, which occur a lot in microelectronics, it's dominated by phonon transport across the interface. And that's what we're primarily going to be talking about today. Again, that finite resistance that occurs can be quite substantial when you look at it in the whole range, especially because there's many interfaces that occur. It is about the equivalent resistance as what you would get if you had a thin film of silicon as big as 0.15 to 15 millimeters thick of silicon. That's the amount of resistance that you get just at that interface. So you don't want to neglect that. So let's talk about the scattering that occurs and how the phonons behave at the interface. Next slide. When a phonon approaches the interface, it can either transport through harmonic interactions, which is a simple transmission or reflection of the phonons when the energy carriers or the density available energy states on either side of the interface have same frequencies, then you can have harmonic transport across the interface. You can also have anharmonic transport, however, where you have multiple phonons combining to a new frequency or a single phonon breaking into multiple frequencies. So you can model the harmonic behavior that occurs using the non-equilibrium Green's function approach, which we'll talk about. But if you use near equilibrium molecular dynamics, then you are also modeling anharmonic interaction. So using these two tools and comparing the results of them, we can probe the type of transport that is occurring at the interface, whether it's harmonic or anharmonic, and look at the relative contributions. So with that, then, let's talk about these harmonic interactions. So this occurs when the phonons maintain their original frequency and are transported through the interface. But this can only happen if there's an overlap in the density of states of the energy carriers in the film and the substrate. So if you look at this diagram, then just that very small overlap area are the only phonons capable of participating in harmonic transport across the interface due to the overlap in the density of states. Compare this to anharmonic interactions and on the next slide, and then we talk about transmission or scattering at the interface where the phonons change their frequency. Now you have many more frequencies available and you can have multiple phonons participating in this process. Previous research primarily done in Patrick Hopkins' lab, who is my PhD student at the University of Virginia and who is now a professor at the University of Virginia. His work has shown really it's 3 or 4 phonon scatterings are the most dominant for anharmonic interactions. Okay, so my lab has really focused on the 3 M's of thermal boundary conductance. That is measuring it, modeling it, and manipulating it. So we'll begin talking about the measurement technique, which is time domain thermal reflectance. So the next diagram shows the TDTR non-destructive thermal reflectance technique. Next slide. This is a widely used technique in the nanoscale heat transfer community, and it's used to measure a wide range of thermal properties. It utilizes a pumped laser source to create a pulse train, a pump and a probe beam. And there's multiple clicks on this slide if you could do that. So that is why the TDTR technique is often referred to as a pump probe thermoreflectance technique. The high energy pump beam is used to deposit energy onto the sample surface, and a lower energy probe beam is focused onto the sample surface to measure the sample's reflectivity. The reflectivity then can be correlated to the surface temperature through a thermoreflectance coefficient. So if you delay the probe arrival relative to the heating event, then you can trace out the temperature curve, the cooling profile as a function of time, as depicted here in this figure. And then the thermal properties of the system can be determined by comparing the data to a thermal model and varying the unknown parameters. So you can use this technique to measure the thermal conductivity of the film, the electron-phonon coupling factor, or the thermal boundary conductance, depending on what time frame you're zeroing in on. So we've used this for a variety of reasons, but for this, we're using it for measuring the thermal boundary conductance. So indeed, the next slide talks about our modeling techniques. So as I've already prefaced, I'm going to use two different techniques, near equilibrium molecular dynamics so that we can get the anharmonic effects, and non-equilibrium Green's functions to get just harmonic effects. So when investigating the thermal boundary conductance, on the next slide, we can use the near equilibrium molecular dynamics, setting up two computational regimes, and we simulate it here. And you can allow for the possibility of anharmonic interactions, but you can also alter the potential that you use. And you can also use a wavelet analysis on the non-equilibrium molecular dynamics results to observe phonon transport, and we'll talk about that. But then you can also model it using the non-equilibrium Green's function approach, which assumes only harmonic interactions. Here we define the thermal boundary conductance in the Landau formalism using non-equilibrium Green's functions, and the conductance depends on the energy of the carriers, on the occupancy of the phonons in the contacts, and on m tau, where m is the number of available modes for transport and tau is the average transmission per mode. And we're going to talk a lot about manipulating m tau. All right, so molecular dynamics calculations of the thermal boundary conductance. So again, we create a heat flux across the computational domain. The atoms are allowed to interact for a finite period of time, and we just apply Newton's law and solve it for each atom's trajectory. This allows us to come to a steady state temperature gradient, which exists at the interface and manifests itself as a discontinuous drop in temperature at the interface. And we use that gradient then to define the thermal boundary conductance, heat flux divided by the temperature drop across the interface. If you click, then as a reminder, this allows for anharmonic phonon transport unless you purposely manipulate the potential that you use. And we will do some purposeful manipulation. So here are the results, or what it looks like when we use that purposeful manipulation. You can use a harmonic potential as the potential between the for the molecular dynamics simulation, or you can use an anharmonic. Most molecular dynamics simulations use a Lennard-Jones potential, and that provides anharmonic effects, but you can also use a harmonic potential. And as a reminder, when we're modeling using molecular dynamic simulations, we're not modeling a particular material system. We're looking for transferable conclusions, which provide insight into general transport across dissimilar interfaces, not insight into a particular material interface. All right. So when we're using the non-equilibrium Green function approach, we begin with quantum espresso results for the interatomic force constants. We use that then, and again, concentrating on that m tau, where the thermal boundary conductance is proportional to the m tau. And so we use this rather complicated expression for the non-equilibrium green function to again give us the thermal boundary conductance. All right, so now, as I said, my goal is going to be to manipulate the thermal boundary conductance. Indeed, the next slide. So I'm going to present the concept of a phonon bridge, which was an idea born in my lab probably almost 2 decades ago. And then we're going to talk about a mass-graded phonon bridge. All right, the concept of anharmonicity in thermal boundary conductance. Previous work in our group has demonstrated the effect of anharmonicity on thermal boundary transport at the interface. We introduced 3 systems here with different levels of anharmonicity. One is a simple Lennard-Jones system that is completely anharmonic. One uses a completely harmonic potential. This is the red results. And the third system allows for just an anharmonic link at the interface between the 2 dissimilar materials. So this was modeled using 40 atomic mass units for one side and 120 atomic mass units for the other side. And this enabled us to look at the relative contributions of anharmonicity. So for the anharmonic system, the thermal boundary conductance increases with temperature in a linear fashion almost, which is a signature of anharmonic processes. But for the harmonic system, the thermal boundary conductance is almost independent, as we would expect. When we added anharmonic bonding at the interface, then just at the interface, there is not much of a contribution. This is the green results here. So the next click, and you will see that we confirm that anharmonic forces are what's leading to an increase in the thermal boundary conductance. But that anharmonicity that occurs just at the interface, which people had hypothesized might have been the major contribution, it really doesn't add that much. So we can extract the position and the velocity data from our near equilibrium molecular dynamics results and then use a technique that we promoted in our laboratory about 15 years ago, the wavelet transform, applying it to phonon transport, to plot the kinetic energy density in both spatial and spectral domains simultaneously. So you see, as the temperature increases in the Lennard-Jones system, the anharmonic system, the atomic displacements increase and the anharmonic forces enable the exchange of energy among modes of different frequency. That is, the rates of inelastic processes increase. This leads to thermalization of the vibrational energy in the argon and heavy argon materials. And the energy is then confined to this high wave number mode, and it steadily relaxes into lower modes, correlating with a drastic increase in the thermal boundary conductance. So all that energy that was in the high frequency modes and the low temperature materials has now been thermalized to lower frequency modes, and this enables better transport across the interface. Compare that to then the harmonic system at the bottom. And as temperature increases in the non-equilibrium system, the energy still remains confined to that high frequency. It's not able to transport across the interface. So indeed, this kinetic energy densities that have been calculated as a function of space and wave number using the wavelet transform enables us to really conclude with the next click that in the anharmonic system, conductance increases due to an increasing rate of thermalization of the excess energy in the high frequency non-transmitting modes to lower frequency modes, which are able to then transport across the interface. All right, so the concept of a phonon bridge. We had this idea, what if we were to add another material to the system? Okay, I've already told you that resistance at interfaces can lead to hot spots. So it would seem that that's a bad thing. But what if we were to put a new material in which had the ability to better overlap the phonon density of states of the material in the film and substrate interface? So if you could increase that overlap area, then the transport across the interface may indeed be enhanced. So with the next click, the intermediate layer has these mediating vibrational properties. So the question was, would that allow for a greater thermal boundary conductance if we're able to enhance the overlap in the density of states? So that's where this work began. The next slide is going to show us what a common temperature profile from our molecular dynamics simulations looks like for a bridged interface. So you have the heat transport across the material on the left, and then you have interfacial transport, and then you have heat transport across the material on the right. So the heat flux is imposed, the temperature is recorded over a period of time, and the average temperatures are what are shown here. So then we use the relationship between the thermal boundary conductance, which is Q over delta T, to get a measure for the thermal boundary conductance. But I want to emphasize here that what we're looking at, as going to be highlighted on the next click, is that the resistance that we're looking at, oops, that's a little weird. The boundary resistance is the resistance from the left side to the junction, plus the resistance of the film itself, because the film, of course, has a finite thickness and a resistance due to its lower thermal conductivity. And then you have the resistance between the junction and the right-hand side. So all three of these resistances then are adding to the thermal boundary conductance. All right. So we use the non-equilibrium molecular dynamics technique, and here are the results for conductance as a function of temperature for both an abrupt interface and a bridged interface. The conductance increases linearly with temperature for the abrupt interface, which is shown in black, which again is the signature of anharmonic processes. But we see that this linear dependence is changed for the bridged interface, and there's a much more rapid increase in conductance as the temperature goes up, the purple diamonds here. This is actually due to a transition from harmonic to anharmonic interactions. So as I mentioned earlier, the strength of the anharmonicity at very low temperatures is weak, but as temperature goes up, it becomes stronger. So this demonstrates that anharmonicity present within the bulk interfacial layer itself also results in an extra enhancement in the conductance across the bridged interface. So what we can conclude from this is the fact that the enhancement in thermal transport that we get from adding an interfacial layer is not only due to the linear enhancement with anharmonicity, but also there's an extra gain due to the transition from harmonic to anharmonic interactions while the layer is present. So next, we tried to understand how the level of mass mismatch in our systems can influence the thermal transport at the interface when you have a uniform interfacial layer present. So we had results already for the 40 and 120 AMU contacts. So then we looked at a higher mismatch, modeling 40 atomic mass units with 240 atomic mass units for the two contacts. First, we look at the conductance axis in these two plots, and we see that the increased mismatch on the right, the conductance values decrease in general, as we would expect. But the important finding here is that our molecular dynamics simulations show that the conductance can be maximized when the added intermediate layer has the atomic mass of the geometric mean of the two interfaces. Next click. So in this case, the ratio of the masses at the two boundaries is the same when you have a geometric mean for the atomic mass of the bridged layer. So we get maximum conductance when the junction mass is the geometric mean, which for physical systems means the Debye temperature of the interfacial layer should be the geometric mean of the Debye temperature of the materials on either side of the interface. So what does that look like, and how might we be able to do that? Well, experimentally looked at platinum on silicon. And with a Debye temperature of 230 for the platinum and 625 for the silicon, the ideal Debye temperature for an interfacial film would be 379. Of course, Mother Nature didn't give us a material with a Debye temperature of 379, but the closest we could get was nickel. So we used nickel as our intermediate layer, and we used metal organic chemical vapor deposition to grow a series of graded layers using increasing thickness. So you see with no intermediate layer, the thermal boundary conductance is represented by the red dot. And we see with a very small nickel thickness, we have significantly enhanced thermal boundary conductance by going from about 110 up to 270. And then as the thickness of the nickel film increases, the thermal boundary conductance decreases to the point where eventually the resistance added by the intermediate layer itself overshadows the increased conductance, and eventually the composite system with the film has a lower thermal boundary conductance than just the film substrate without an interfacial layer. So for thin interfacial layers, indeed, we have shown that a properly chosen phonon bridge can increase the overall conductance in the system. Next slide. So let's model this, and let's model a really ideal system where now the bridge is not a single material, but instead it's a series of materials with a smooth transition from material A to material B. So this can preserve the overlap and the respective phonon density of states, and the mixed interfaces open up additional modes of transport. Increasing the M tau is what we're doing with this. So each of our interface, we apply our geometric mean rule to, and we can look at various numbers of interfaces added in various thicknesses as well. So we'll be adjusting N, and we'll be adjusting T, the thickness of each interfacial layer, and looking at the results. So simulations using our mass-graded phonon bridge are shown here. And again, we extend the idea to multiple layers with the enhancement. So this is the result with 4 layers, and each layer is 2 unit cells thick. So the total layer thickness is 8 unit cells. And with the next click, I can show you the results then. We see that applying the geometric the exponentially mass graded interface with the geometric mean rule, we see what the conductance looks like. And the results are shown on the next slide then. So we have 3 factors that are going to affect the transport at the mass graded interface. One is just the temperature, which controls the strength of the anharmonicity. The other is the thickness of the layer, which determines the available space for the anharmonic phonon-phonon interactions to occur. And then the third is going to be the thickness, or the number of layers as well. So we used our non-equilibrium Green's function simulation, and the next click is going to show you what the thermal boundary conductance looks like with various thicknesses from 1 unit cell to 6 unit cells and various number of layers of thickness. And with the next click, you can see that you get to saturation very quickly with the number of layers. All right, so just at 4 layers, we've actually saturated. So you have better vibrational matching and with these multiple layers, but the thermal boundary conductance does saturate just after a few layers in the harmonic regime. All right, so when anharmonicity is weak, as shown here at low temperatures, we see that increasing the number of layers causes a linear increase in the thermal boundary conductance. But there is really an insignificant effect for the thickness, or equivalent to the number of layers for each line. So better vibrational matching is not responsible for this linear increase, but it's the extra anharmonicity provided with with greater thickness within the film, as we've talked about before. However, if we look at high temperatures with the next click, which is when anharmonicity is strong, one more click, we will see that the thermal boundary conductance actually reaches a maximum and then it starts decreasing. This is the onset of the intrinsic resistance within the film itself, which is overshadowing the enhancement that we see. So with the next click, this onset of the intrinsic resistance overshadows our enhancement. So we look at better vibrational matching is not responsible for the linear increase. It's the anharmonicity provided by the greater thickness in the film. But as the film thickness increases, the resistance of that film overshadows this enhancement. All right. So a summary of our findings then. We have better vibrational matching with increasing number of layers, and that always helps. But we have contradictory results for the effects of anharmonicity. When anharmonicity is weak at low temperatures, then greater layers thickness help rethermalize the phonons and enhance the transport. But when anharmonicity is strong at high temperatures, the intrinsic resistance due to layer thickness overshadows the enhancement. So, adding mixing to a perfect interface on the next slide can result in an increase in the thermal boundary conductance. This happens due to symmetry. The phonons that cross a perfect interface have to conserve their transverse momentum, as shown in the diagram on the left. But if you were to have random mixing added at the interface, as shown on the right, then the symmetry of the system is lost, and the phonons flowing through the interface do not have to conserve their transverse momentum. So next click, the central figure is going to show an example of this phenomena for a simple cubic lattice. The y-axis is the conductance of the mixed interface normalized by the conductance of an abrupt interface, and the x-axis is the average mass of the mixing layer. By adding mixing at the interface, you actually open up new transport channels, m tau, that may result in larger thermal conductance. So how do we experimentally begin to look at a mass-graded interface? So we took platinum silicon, deposited it by PVD sputtering on a silicon substrate, and the material was then annealed in a vacuum environment with various temperatures, and it induced mixing at the interface. And then our XPS results were able to show that the interface slowly transitioned from platinum silicon to silicon through a series of intermetallic compounds. So this is looking at that mass grading experimentally. It's one way of advancing the field. So the measurements of the thermal boundary conductance here indeed show that the increased mixing layer thickness caused enhanced conductance across this interface. So the conclusions of this work. A mixed interface can help. So phonon engineering, I would say, is a developing field of study. It's complicated because phonons are bosons. They follow Bose-Einstein statistics, as opposed to it being much easier if we were only dealing with electrons, which are fermions, obeying Fermi-Dirac statistics. So phonon transport across interfaces is complicated by this broadband nature. But we have demonstrated the utility of bridging layers using a geometric mean rule. We have shown that exponentially mass-graded layers can further push this enhancement, and the increasing number of layers results in better vibrational matching. And I would say we are only just beginning, and I just noticed I'm a little bit over time. I apologize. The next slide is just some a chapter I published on contributions of women to nanotechnology, and a chapter in this book details the work I'm talking about here, engineering interfaces at the nanoscale. And then the next slide is the As Promised chapter that is just coming out, and this link is available for download until mid-January, when the book Advances in Heat Transfer will be coming out. So with that, I'd like to thank you all for your attention and my contributors for their partnership. And I'm happy to take questions, although I am over time. I apologize. Length and time scale at which TDTR experiments are conducted match with the length and time scale at which near equilibrium can the length and time scale. We are certainly matching the length scales. The time scales near equilibrium molecular dynamics, they come to a steady state when we're measuring that. So I don't believe the time scales are appropriate there. We certainly can do TDTR in a time scale, which enables us to extract thermal boundary conductance though.
Okay.
And then what if we have a flowing?
Norris, I mean, I should have thanked you, before you started taking the question and answer. It was a very interesting talk, and I would request the audience to please type in their questions through the Q&A chat box that is available for you. And it would take a minute delay for us to get the questions to the Zoom link here. But meanwhile, I think we already have a few questions coming from participant Abhijit. I will just read out the second question for you, if you may permit me, or yeah. So the second question is, what if we have a flowing fluid at the interface? In that case, how can we modify the phonon theory and account for the convection and the diffusion as well?
Interesting question. Of course, a flowing fluid would not have phonon states in it. The phonons are the vibrations of the crystalline structure. However, in Professor Patrick Hopkins' lab, he has looked at some fluid solid interfaces, and I have not been following that work, but so the phonon transport would not be applicable in that case.
So he has another question. How do you compute the transmission accurately when anharmonic effects are present? Since the density of states only accounts for harmonic phonons, the overlap may not capture all the heat transport, right? So shouldn't we make some modifications to the model for heat flux equations?
Trying to follow.
Yeah, it's a very complex question. I think it has multiple questions inside that.
I think there are too.
Yeah, so I think he tries to ask, how do you compute the transmission when anharmonic effects are present? So that's accurately, I mean,
yeah, so the using the near equilibrium molecular dynamics approach, you can adjust the potential to have either harmonic or anharmonic effects. But if you're using the near equilibrium Green's function approach, then that's where you calculate m tau, and then you cannot influence the type of interactions that are occurring. You're only going to have you're only going to have harmonic interaction. So I'm unaware of a non-equilibrium Green functions approach that would allow introduction of anharmonic effects. You're always going to have the harmonic effects. I think might be where we're getting at there.
Okay, thank you. And the other question he has is, when we talk about the anharmonicity, what temperature are we talking about, and how these two are correlated?
Yeah, so it's not a real material system. So we modeled 2K and 30K in our molecular dynamics simulation, but temperature doesn't correlate to an actual temperature in a real material system. So then isn't the film having a temperature gradient rather than a uniform temperature? Of course it is, yes. Is it the Debye temperature? So it's the way the molecular dynamics simulations work, there is a temperature that is generated, but it doesn't correlate to a physical temperature, I think is the question.
Right.
It would depend on the material system, what temperature that might begin to correlate. So we're just modeling argon, heavy argon, again, not trying to get a particular material system, but generally transferable results. So high temperature, low temperature, it's relative and it's not an exact physical temperature.
Thank you, Professor Norris. As of now, we have only these 4 questions. We'll just wait for a minute or two until we receive some more from the audience. So meanwhile, I just want to ask you this, so this kind of work where you are trying to tune the semiconductor material by introducing the phonon bridge and trying to improve the conductance and so on. So how practical is it to extend this to different kinds of materials? Right now you have talked about, I think, a particular material where you have matched the geometric mean, with particular Debye temperature material with a similar Debye temperature, but in other cases where you can't get a match of the Debye temperature. So how do you go about with this kind of a phonon bridge concept?
Yeah, so you're asking, it's great. We studied this theoretically and we can model and we can adjust things the way we desire to adjust them. But in a practical sense, in my laboratory, we have both theorists and computational people doing theory, and then I have experimentalists as well. And the experimentalist is funny. Sometimes they transition from an experimentalist to a modeler because they get frustrated by the fact that they can't get a material system with where it's easy to decouple the competing effects, because in a practical material system, you don't have that perfect interface, you don't have the perfect overlap in the Debye temperatures, you don't have, crystalline structures that are perfect at the interface. There's always mixing. So it's funny to watch the transition of experimentalists sometimes to computational scientists because they're frustrated by that. So, certainly using very advanced deposition techniques, you can begin to elicit that perfect interface. And I think we would be naive to think that the semiconductor industry is going to invest to have these perfect interfaces with the exact properties that we are modeling. However, if we can begin to understand the fundamental physics advance, in the field and what happens at the interface, I believe that semiconductor manufacturers can use that guidance when they're envisioning a stack to talk about and think about the intermediate layers. And in fact, adding an intermediate layer, another film, might enhance the overall performance of the stack. So it's never going to be, what we predict as the geometric mean is best, and you should have 4 layers of 2 unit cell thickness. That's not going to happen. But that fundamental understanding of the interface, and even understanding that actually intermixing at the interface enhances conductance, which was counterintuitive. Oftentimes you would think a perfect interface without the mixing is the best way to go.
Okay, thank you. The kind of phonon bridge here you are talking about is applied to both the semiconductor metal interconnects as well as semiconductor interconnects, right? It's a generalized one, or is it?
No. Well, let's think about that for a minute. We have not examined a semiconductor interface. We've always focused on a metal semiconductor interface, but a semiconductor interface would be all phonon transport as well, and not something I've thought about. We haven't advanced that field, haven't thought in that way yet. Oftentimes it's the metal semiconductor interface that has the highest resistance.
Okay.
Because much greater disconnect in the density of states.
Right. And how difficult are these experiments to verify the conductance? So you showed you talked about the fabrication using PVD, and then you showed the results of conductance. So how accurate are they, and what is the kind of resolution that you get when you measure these conductance values experimentally?
Yeah. The let's see. I can't remember if any of my
You just use the
results showed.
TDTR technique, but I was just wondering about the sensitivity or the resolution of these TDTR
Right.
measurements. Sure.
Yeah. Error bars are fairly small, and I was just looking to see if I had any of my results with error bars on.
Yeah, you have one, I think, probably where you show the
Platinum
geometry.
silicon.
Yeah, right. The
Yeah,
platinum silicon.
yeah. So that gives you an indication. That's I think on slide 29 gives you
Right.
an indication of the error bars. So it's
Also
they are
22,
difficult
I think.
experiments, but the error bars are fairly tight. That's from repeatability.
Right.
So it's measuring different spots on the surface, and repeated measurements on the surface is how those error bars are calculated. So if you're enhancing by, from 100 to 250, that's a real thing. The error bars are less than that,
Yeah.
but the error bars are significant.
Yeah. So I think that's it, I would say, because we are not getting any more questions from the audience, and I would like to then conclude the session by thanking the speaker for an excellent talk and a very detailed exposition on the current research on the phonon bridge, especially, and giving her point of view on all the questions that was asked. So thank you so much, Professor Norris, for the excellent talk, and also thanks for joining on a weekend. I know it's a difficult time, but you could, put in some 35, 45 minutes on this particular conference, and we appreciate that. And we would like to get participation in maybe a future ISHMT ASTFE conferences that we organize in a couple of years from now, and we look forward to a hybrid, or if you like to come and visit us, we are welcome to have you here. So
That'd be wonderful.
Thank you so much once again for this particular talk. Thank you so much.
Wonderful. Y'all have a great day. I hope the conference is a great success. Thanks for having me.
Thank you, Professor, and wish you Merry Christmas holidays that are coming up, and also season's greetings and Happy New Year to you.
Indeed. Happy holidays and Happy New Year, everyone.
Thank you so much. Thank you. Bye-bye. So I think we just conclude the particular session, keynote talk by Professor Pamela Norris. And with this, we conclude all the sessions for the day. And we will meet again tomorrow for the third day of the conference. We will begin with talks, oral sessions, and keynote talks. So please join again tomorrow for the third day of the conference. Thank you so much.